Okay, so let's look at these questions. Which point on the graph represents the parachute opening? So we presume that this is the velocity time graph of a parachutist. So let's look at the story it tells. As we go along in time, the velocity starts out at 0 but increases and increases and increases, but eventually it actually levels off, and so at about 55 metres per second the velocity becomes about constant until something happens at C and the velocity drops off dramatically down to only 8 metres a second at D, and then again right at the very end it drops down suddenly to 0. So the primary point of a parachute is to reduce the velocity of the parachutist. So where is the point where the velocity gets reduced the most? Well, from here to here. So C is the answer. Question 2 asks, this speed time graph shows the speed of a skydiver. Which letter shows part of the graph where the acceleration is 0? So remember that in a speed or velocity time graph, then acceleration is equal to the gradient. So at point A, the gradient looks like this. At point B, it's a tangent to the curve, looks like that. At point C, the gradient looks like that. But at point D, the gradient is pretty much horizontal. So certainly at A, the gradient is not 0. The acceleration is not 0. At B, it isn't 0, neither is it 0 at C. But at D, the acceleration or the gradient is 0. So the correct answer is D. Question 3. Which of the following speed versus time graphs shows an object which is accelerating at a constant rate greater than 0? So remember, when we've got a speed versus time graph, then acceleration is equal to the gradient. So let's look at the gradient. We're looking for a gradient which is constant and greater than 0. So the gradient of A is indeed constant and greater than 0. So A is definitely a possibility. The gradient of B is in fact 0. So therefore it's not greater than 0 and it can't be B. Now the gradient at C is interesting. It starts out looking like that, but then at this point it's like that, and at this point here it's like that. So the gradient is actually changing, therefore it's not constant. And the same way here, the gradient at this point looks like that. At the top it's 0, and then on the other side here it goes the opposite way. So again it's not constant. So the only one in which it's constant and greater than 0 is A. Question 4. Tom went for a bicycle ride. His speed versus time graph shows his speed during the journey. So what was his fastest speed during the trip? Well, you just read this off the graph. What is the highest speed that's reached? 10 metres per second. Between which time points was Tom at rest? Well, when Tom is at rest, his speed is 0. So all this question is asking is, when is Tom's speed 0? So it's 0 at the start, at t equals 0. And then also between points C and D, which corresponds to the time between 13 seconds and 16 seconds. What is Tom's final speed? It's pretty simple. At the end of the graph, what speed? We simply read it off. That would be 5 metres per second. Now D is a little more tricky. Calculate Tom's acceleration between 0 and point A. Now because this is a speed versus time graph, we know that acceleration is equal to the gradient. And gradient is equal to rise over run. And in this case, that's going to be the change in speed over the change in time. So looking between point O and A, the change in speed, the initial speed, or the final speed, let's say, so the speed at A minus the speed at O, that's the change in speed, divided by the time at A minus the time at O. So the speed at A is 10 metres per second. The speed at O is 0. The time at A is 5 seconds. The time at O is 0 seconds. So 10 minus 0 is 10. 5 minus 0 is 5. So our answer, 10 divided by 5, is 2 metres per second squared. Because here it is metres per second, and then we're dividing by seconds again. So it's metres per second squared. Now here, this question, multi-flash photograph, is very similar to a ticker timer in that you've got information being recorded at a constant rate, let's say. And here it says here once every second, and the measuring tape shows 0.1 metre intervals here. So let's have a look. What the things with a ticker timer or with this multi-flash photograph is that when you've got data being recorded at a constant rate, then the distance between points indicates the speed. So here you can see between the first 2 points we've got a distance of about that, and then the distance between the next 2 points is a bit larger, and the next 2 points is even larger, and the next 2 points is even larger. So here we've got a situation where the velocity is increasing. The speed is increasing as from this point to this point, because the distance travelled between this point and this point is smaller than that between that and that. And then again, this one is even larger than between the previous 2 points, and between here and here is even larger than the previous 2 points. But note that this distance here, and this distance there, and that distance there, and that distance there, and that distance there, they all look about the same. So from this point to this point, it looks like the velocity is constant. Actually, it even looks like it continues all the way to here. But then have a look here. The distance between these 2 points, or these points here, appears again to be constant but slower. So again here we've got V is constant, but we'll say it's slower. So now let's have a look and see if we can find a graph that matches up with that. Because that's what we were asked. Which graph best represents the velocity of the ball as a function of time? So this first graph has our velocity increasing, and in fact always increases. And we can see that in fact that's not the case, is it? Because it does increase here. Here it's constant, but here constant fast, let's say. And here is constant slow. So clearly the velocity doesn't go down here, so this cannot be correct. This one has the velocity increasing, which corresponds to what we see here. But then we've got a constant velocity, not zero velocity. When the line is going here in a velocity time graph, that's representing zero velocity, which would mean our dot would be staying, our ball would be standing still. So it's definitely not that one. Again, this one here doesn't have the increasing velocity, so that bit's not right, but also this one has a section of zero velocity, which we don't have here. So again, that one's not correct. This one, we've got an increasing velocity, and then we've got constant velocity, and then we've got a drop off to another constant velocity that is less. That does correspond to the story here, where we've got an increase in velocity, a constant quick velocity, followed by a constant slow velocity. So D is the correct answer. This one's quite tricky. What it requires you do is to read the story and write your own graph and see what corresponds to it. So the command module speeds up to leave the Earth's gravity. So we know that we can draw our own one down here. So the command module speeds up. So presumably it starts at some speed, it gets faster. And at a certain time p, it reaches a constant speed. So if it's a constant speed, it's going to be horizontal in a speed-time graph. And then it's heading for the moon. When it reaches the moon at time q, it slows down. So that means the velocity is going down again by firing retro rockets. At time r, it moves at a constant speed. Remember, constant speed is going to be a horizontal line while orbiting the moon. At time s, it fires its main engines and speeds up. So again, the speed is getting higher to leave the moon's gravity and returns to Earth. So, which graph shows the motion of the command module? Which one looks like our one? Well, that one isn't correct because it says that at r, there's no constant speed at r, and yet here it said at r, it moves at a constant speed. So we know it's not this one. B, here we've got increasing speed, constant speed, increasing speed, constant speed, increasing speed. And yet here we have a time when it said it slows down. There's no slowing down here. The speed is always either increasing or staying the same. So it's not that one. C looks very similar to what we have. So I suspect that's correct. Let's have a look at D. D is very similar, except at S, it is slowing down. So let's have a look. At time S, it fires its main engines and speeds up. So clearly this little part here is not correct. So the correct answer is C. Okay, final question. The graph shows the speed of a car when it is in different gears. So from the information in the graph, which of the following statements is correct? Now notice that many of these statements include the word acceleration here, here and here. And here it's talking about a net force, which you will learn later that force is equal to mass times acceleration. You'll learn that next lesson. Anyway, so basically each question is talking about acceleration. So it's really important to see what's happening with the acceleration at each of these points. So remember, acceleration in a speed versus time graph, hopefully you remembered this by now, is equal to the gradient. So notice the gradient here is quite steep. Here it's a little less steep. Here it's even less steep, and again even less steep again. So you can see that in first gear we've got a high acceleration, then lower acceleration, and even lower acceleration. So let's have a look at the possibilities. As the car's speed increases, its acceleration decreases. So here, as the speed increases, the acceleration decreases. That seems like it might be correct. B, the car experiences greatest acceleration in fourth gear. Well, actually the gradient is low in fourth gear. So this one is clearly not correct because this gradient is less than that gradient. So therefore its greatest acceleration is definitely not in fourth gear. This says the car's top acceleration was approximately 140 kilometres per hour. Well, we don't even have to bother doing the maths here because the units are incorrect. Acceleration is talking about a change in velocity or a change in speed over time, and therefore that the units are going to be, for example, meters per second, or in this case it might be kilometres per hour, but these units are the units for speed, not the units for acceleration, so that is clearly incorrect. D, the greatest net force, so that would mean the greatest acceleration, is when the car is in fourth gear. So in fact that's pretty much the same question as B. In fourth gear the acceleration is actually the least, and so the force, which equals mass times acceleration, seeing the mass of the car doesn't change, the acceleration being the least means the force will also be the least. So that is not correct, and our correct answer is A.